So the problem consisting of a uniformly distributed load is now treated as a Rayleigh Ritz problem wherein the potential energy has been formulated. The potential energy in the bar is AE, strain energy plus work potential. Strain energy is given by AE by 2 integral over the length dou U by dou x whole square with respect to x, and work potential term, if I am determining work potential term, and that is equal to, that is important in this problem, that is it is acting over the entire length 0 to L q into u dx. So q is the force which is causing the bar to get displaced by an amount u with respect to x. So this is the important step in the problem. You have to remember how we have to write the, how we are supposed to write the force term or work potential term. Remaining is just simplification like in the earlier cases. Pi work potential now is equal to strain energy divided by 2, that is, sorry, AE by 2 integral over the length dou U by dou x whole square with respect to x, that is strain energy, minus integral over the length C into x into U dx. Right? So is there any difficulty till here? Is there any difficulty till here? Please
No,
answer.
sir.
Okay.
No, sir.
Now, second step is we have to assume a polynomial function for the displacement u. A function should be assumed, or a mathematical model or an equation should be responsible, or it should give us how u varies. U ಯಾವ ರೀತಿ ವೇರಿ ಆಗುತ್ತೆ, ಇಟ್ಸ್ ಅ ಲೀನಿಯರ್ ಫಂಕ್ಷನ್ ಅಂತ ನಾವು ಫೈಂಡ್ ಔಟ್ ಮಾಡೋಕ್ಕೋಸ್ಕರ ಒಂದು ಈಕ್ವೇಷನ್ ಫಾರ್ಮ್ ಮಾಡೋದು. So I told you, whenever we assume a displacement function, it should obey the boundary conditions of the given problem, and it should consist of the convergence requirement. What it is? The first one is the rigid body displacement. Therefore, A0 term will be a constant. Then A1x, you have A1x here, A1x. That means it's a linear term that will give us constant strain state. Therefore, I think this is enough. Two terms are enough to get solution for us. So I will stop with A0 plus A1x. Clear? Now, once we have assumed this, we have to find out A0 and A1 from this. So for that, we have to assume the boundary conditions. So from figure, it is clear that two boundary conditions are possible. What is it? The displacement is u is equal to 0 at x equal to 0. This is one condition we know. Displacement u is equal to 0 at x equal to 0. The another condition, displacement u is maximum, that is equal to L at x equal to L. So whatever be the displacement u, that is u max or u, right, at the free end. So taking these two things in consideration, we will apply in the formula. What it is? When we substitute the condition x equal to 0, u becomes 0. Obviously, in the equation, what will be 0? A0 will be equal to 0. U equal to 0, that's equal to 0 plus A0 plus A1 into 0, or A0 is equal to 0. This is one thing we understand, but you have to substitute and find out. Then, therefore, now our equation is now u equal to A1x. U is equal to A1x, and we are interested in finding the Rayleigh Ritz parameter A1. Okay. Now, differentiating the above equation with respect to x, what do we get is dou u by dou x, partially differentiating with respect to x, it is A1. Now, the third step is substitute the displacement function into potential energy functional. You have to substitute in the displacement dou u by dou x in this equation. Dou u by dou x is now substituted in the total potential energy equation, and substitute what is u equal to. U is equal to A1 into x. U is equal to A1 into x, and dou u by dou x equal to A1. Right? Now, so once I have this, I have to apply the principle of minimum potential energy. What is the condition here? What is the condition for the potential energy to be minimum? Dou pi by
Dou A1 equal to 0.
dou pi by dou A1 should be equal to 0. That means for the potential energy to be minimum or the function to be minimum, we have to find out pi value and derive it with respect to x. Now, substitute in the equation pi equal to ae by 2. Instead of dou u by dou x, substitute a1, that is a1 square into with respect to x, c into x, that is a1 into x with respect to x, a1 square with into a1 square with respect to x minus p force is given by q force is given by c into x. Now again u is equal to a1 into x in the work potential term. In the work potential term it is c into x into a1 into x, right? Now this is nothing but a1 is constant term into c into x square, right? Now integrating the above equation, what do we get? Integrating the above equation, ae by 2, a1 square, take it outside, integral of dx is again x, integral of 1 with respect to x is x, between the limit 0 to L. Then c and a1 are constant, take it outside, integral of x square is x to the power n is what? X to the power n plus 1 divided by n plus 1, therefore it is x cube divided by 3, x cube divided by 3. Is the integration clear?
Yes, sir.
Between the limit 0 to L. Now substitute the upper and lower limits. In the first term, we will get only L minus 0, that is equal to L. In the second term, what we will get is x cube by 3, you take 3 outside, L cube minus 0 divided by 3, that is capital L cube. Now total potential energy term is now pi equal to A1, AE by 2, A1 square into L minus C into A1 into L cube divided by 3. Now this equation is important for us because we are differentiating this equation with respect to A1 and substituting it equal to 0 for potential energy to be minimum. Clear? Now let's come here. We have to minimize the potential energy functional. What is the condition? Dou pi by dou A I equal to 0. We have only one Ritz parameter, therefore dou pi by dou A1 equal to 0. Now the function pi we have written equal to ae by 2, a1 square into L minus c a1 into L cube by 3. Substitute the value of pi with and differentiate it. Dou pi divided by dou a1, that is equal to ae by 2. Differentiation of a1 square will be 2a1 into L minus differentiation of c L cube by 3 is as it is, and differentiation of a1 with respect to a1 is again 1. Differentiation of a1 with respect to a1 is 1. Differentiation of a1 square is 2a1. Substitute the whole thing to be equal to 0. Substituting the whole thing to be equal to 0. So what we get out of this is this 2 gets cancelled. This will be left with ae into a1 into L minus c L cube divided by 3. Transfer CL cube by 3 to the other side. This becomes plus CL cube by 3. Then AE into L will be transferred to the denominator. AE into L is transferred to the denominator on the right hand side. A1 is retained on the left hand side. So what we get is C L square divided by 3AE. C L square divided by 3AE is what? The Rayleigh Ritz parameter A1. So this generalized coordinate or A1 Rayleigh Ritz parameter we have found out. Now making use of this A1, substitute in the earlier equation, that is you have to find displacement of the given problem. That is the question asked. U is equal to, what was U equal to? U was equal to A1 into X. U was equal to A1 into X. The displacement is a function of X, that is as X varies, U also varies. Now substitute whatever A1 we have found out here, substitute A1, whatever we have found out here, C into L square divided by 3 into A into E multiplied by X. 3 into A into E divided by 3 into A into E into X. C L square divided by 3AE into X. Then, so what we are supposed to do now with this? Determination of displacement. What are we supposed to do? Whenever I substitute the value of X, what happens here? Whenever I substitute the value of X, what happens here? The displacement will be obviously 0. Right?
0.
Right? And when it is maximum, when X is equal to L, that is CL
L.
divided by 3AE. Right? So C is a constant, say 10 kilonewton force into L cube. L may be 10 meter divided by A, area is given, Young's modulus is given. So I can substitute the value as correspondingly equal to so and so. So this is how we obtain the displacement whenever a uniformly distributed load is given. Right? So the very important thing in the problem is, we have to find out how the displacement is given or the force is given for writing the work potential. That is, a uniformly distributed load is given. So the only thing you should be keeping in mind in this problem is work potential term, how to write it, that is integral over the length Q into U dx. Q is the force given, that's equal to Cx, into U is the displacement due to force with respect to x. So is the problem clear to everyone?
Yes, sir.
Yes, sir.
Okay. So can we move to the next problem?
Yes, sir.
Now the next problem is all about when a body force is given. The next problem is all about when a body force is given. What we are supposed to do when a body force is given. So use the Rayleigh Ritz method to find the displacement at the midpoint of the rod shown. Now see here, they have mentioned body force equal to 1. F is the body force equal to 1. That means that is the force acting over the entire volume. It is acting over the entire volume. So volume here, it's a one-dimensional problem. It may be considered as area into length dx. So dx as it varies, right? So it's a one-dimensional problem, means the displacement is possible only along x direction, or number of parameters required to represent the body is only x.